Hello class, and welcome to the introduction to vertical block oscillators. First, a quick review. We learned yesterday that there's this thing called simple harmonic motion. In simple harmonic motion, stuff moves back and forth and back and forth and back and forth in a nice regular manner, which means that we can describe how it is oscillating using a period, a frequency, and an amplitude. Ooh. Alright, all sorts of crazy stuff when this is a spring, where the big force that we care about is the spring force given by Hooke's law, called the restoring force because it always restores the spring to its natural length. Now, in a horizontal block oscillator, the natural length also gives us its equilibrium position when it is oscillating. This means that it's going to oscillate around the equilibrium position, which is given by the natural length. Now, the other big thing is the conservation of energy. We have two types of energy here, kinetic and elastic potential energy. And it jumps from one type to the other and back and forth and back and forth and back and forth for each displacement x incrementally as it goes. Awesome. Cool stuff. And period, frequency, they're inverses of each other, given by this nifty set of equations. Alright, cool. Notice that the only thing that determines period and frequency is the mass of the block at the end of the spring and the stiffness of the spring itself. The amplitude doesn't matter. Think about what that means for a second. That means if I have a spring and I pull it a foot, it'll have a period and a frequency. If I take that same string and pull it a mile long and let it go, it will have the same period and the same frequency as before, which means it's moving much, much faster. All right, cool. Cool stuff, cool stuff, cool stuff. So, let's look at what we know here. Let us say that we know what the natural length of the spring is. It's given by L. We're going to call this distance here L. We also know the mass of the block. We know the spring constant of our spring. And we know the amplitude. Where here is the equilibrium position of the block, and it is oscillating around it like this. So when it's furthest to the right, it looks like this, and when it's furthest to the left, it looks like this. I'm going to add something to this in a different color. I'm going to add the force. Now, if the block is in this position right here, the spring force is going to push it that way. When it's at the equilibrium position, there is no spring force. And when it's here, my spring force is there. The spring force always points towards the natural length, towards the equilibrium. All right, so now what I want you to do is I want you to, in a moment, pause the video. And I want you to fill all this out to the best of your ability. Fill out all of this in terms of L, M, K, and A, and nothing else. All right, when I say go, I want you to pause. When you're done, unpause, and I'll walk you through my justification. Pause. Unpause. All right, now I'm going to go through my justification. If you do not need the justification, you just want to jump to the answer, fast forward through this bit. All right, we'll start here because it's nice and easy. Here, x. X is defined as the displacement from the equilibrium position, the displacement from the natural length. So, right here, x is 0. which means that the elastic spring energy is 0. Okay, which means that the speed is, I don't know, something or another. The k, well, that's going to be 1/2 mv squared. Ooh, but that's no good because I have it in terms of v, and I need it in terms of this stuff. All right, so I'll come back to that. F net, ooh, I know that one. It's 0. All right, so I got some work to do here. I'm going to jump over here now. X. Let's see, the displacement here, well, that's going to be A. That's going to be the amplitude. It's going to be the amplitude to the left, so I'm going to slap a negative on it, though it doesn't particularly matter. That's just to remind us that there is some directionality going on. Elastic spring energy. Well, that's given by 1/2 kx squared, where the x in this case is A. All right. At this point, the speed is 0, k is 0, and the net force is equal to the spring force, so it's positive k a. Ooh. So I know what this is now. Conservation of momentum. So the total amount of energy here, conservation of energy. The total amount of energy here must be equal to the total amount of energy here. So, since this is 0, this must be this. Which means I can now solve for v, can't I? Alright, well, let's look at this. 1/2 mv squared, I gotta solve for v. Well, my 1/2s cancel out, leave me with mv squared equals ka squared, which is going to give me v equals the square root of ka squared divided by m. Ooh, fancy. Alright, now we're over here. X is positive a. The elastic spring energy is, again, 1/2 ka squared, which means that's 0 and that's 0. And this is now negative ka. Alright, period and frequency. Well, let's see. Period is going to be 2 pi mk. How I remember that is the period mk. Do you know how to solve the period mk? Okay. Done. Frequency, I just remember that it's the upside down version. If you have a better memory device to use to remember that, feel free to use it instead. Alright, so, there we go. Energy and speed analysis of a horizontal spring oscillator is now done. Showing us how the force, potential energy, kinetic energy, speed, and displacement all depend on A. Notice we didn't use natural length here at all. Alright. Now, what if I turn this upside down? So this is still a block of mass m, it's still a spring of spring constant k, but I've flipped it upside down, or sorry, on its side, so now it's vertical. We gotta worry about gravity, which means that there's a gravity force on my block. So here it is initially, and, well, what's going to happen to it? Here x equals 0. What's going to happen? Well, it's going to stretch. It's going to stretch some distance x. Huh. What is that distance x? That distance x? Please solve it for me. Algebraically. Have you done it yet? No? Then pause it. Unpause it! Alright, so. This is going to stop moving when the net force on it is 0. Which means that gravity force is going to be equal and opposite to the spring force. Which means that mg is going to be equal and opposite to the spring force. Notice that I left off the negative because it's opposite the spring force. Which means I can solve for x mg over k. Yay! How long will it stretch? It'll stretch mg over k meters. All right. Doing well. Here's the hard part. Here's the part you're not going to like. Here we have a vertical block oscillator oscillating around its new equilibrium position. Here, I'm going to label that differently. Actually, no, I'm not. That's my equilibrium position. This right here, that's its natural length. This is the absolute top of its oscillation, and this is the absolute bottom of its oscillation. Notice that I am measuring from the top of the block, so all I'm really caring about is what the spring is doing, not the block. Because I don't care what the dimensions of the block are. I care about how the spring is stretching and compressing. Alright, now other stuff. Over here, we're going to do some labeling. Where this bit right here, this distance, that's called x top. This distance right here, that's going to be called x equilibrium. This distance right here, that's going to be called x bottom. Ooh, interesting. Where, of course, that's L. Alright, other things we know. Oh, well, we know what this is. That, by definition, is the amplitude. Which means that that is that. And that is all the help that I am giving you. Alright, what I want you to do for the rest of class, because it just might take you that long, I want you to fill out this table that I have in front of you. I want you to, in terms of L, M, K, and A, and with the stuff I've given you here as a hint, I want you to tell me what is the displacement of the spring at each of the three positions, what is the potential elastic energy at each of the three positions, what is the height, where height is measured from here. So, here, I'll give that to you. That's height. That's height, and this would be h equals 0. Give me the gravitational potential energy of each of the three positions. Give me the speed at each of the three positions. Give me the kinetic energy at each of the three positions. And give me the net force at each of the three positions. One more hint. The equilibrium position is not the same as its natural length when it is a vertical block oscillator. Huh. I wonder what the new equilibrium position might be. Alright, there you go. I've given you all the hints you could possibly want. Go.